All right, it is 2. So if you could please type here in the chat window to let me know that you are present. Thank you all. So what we are going to be doing today is formalizing how we are going to perform circuit analysis in the frequency domain. So let's write that down. All right, so when we have a sinusoidal voltage signal, we can express it in the form V of t is equal to Vm cosine omega t plus some phase angle theta v. And similarly, a sinusoidal current could be expressed in the form Im cosine omega t plus theta I. These representations are what I refer to as time domain signals, voltage and current. We learned yesterday that we can get the same analytical results of doing analysis using time domain signals if we use an exponential representation of those, or excuse me, an exponential complex number representation of those signals. So we used V of t was equal to Vm e to the j omega t plus theta v, and I of t was equal to Im e to the j omega t plus theta I. This is what we were doing at the end of our last class meeting. And I'm going to call that the mixed domain representation of our signals. What we are going to be dealing with today is the frequency domain representation of our signals. So in the frequency domain, we are going to represent a voltage as V with a bar over it for a complex number, where V is simply Vm angle theta V. And similarly, our frequency domain current will be I, which has a value of Im angle theta I. So this is really the same information that's contained in our mixed domain and time domain signal representations here, except for one very specific caveat. When we work in the frequency domain, we effectively are just throwing away the e to the j omega t portion of our signal. The reason that we're doing this is because it is redundant information. If our signal is excited using a sinusoid at one particular frequency or one particular value of omega, then any response that we could be interested in will also have that same angular frequency. So this frequency domain representation just throws away that redundant information. These representations are called phasors. A phasor is just a shorthand notation that electrical engineers have developed to represent time domain signals. And we get our phasor representation of a signal by simply keeping the magnitude, keeping the phase angle, and throwing everything else away. So, as an example, if we had a time domain voltage, VA of t was equal to 14 cosine 9t plus 18 degrees volts. The phasor representation of this voltage would be VA is equal to 14 angle 18 degrees volts. If we had a current IB of t was equal to 3 sine 6t plus 30 degrees amps, we would have to convert this sine function into a cosine function by subtracting 90 degrees from the phase angle. And then we could convert it into the frequency domain simply by keeping the magnitude of 3 and the phase angle of minus 60 degrees. So converting from the time domain into the frequency domain is literally this easy. We just need to make sure that our signal is expressed as a cosine with a positive amplitude, and then we keep the magnitude, keep the phase angle, throw everything else away. Okay. So this is a critical large step in understanding our frequency domain circuit analysis. What we're going to look at now are phasor representations of our current and voltage relationships for the circuit elements that we're familiar with. So let's talk about resistors. Let's say we have simple resistance R over which a sinusoidal voltage V of t is applied and through which a sinusoidal current I of t flows, where V of t is generically of the form Vm cosine omega t plus theta v, and I of t is generically of the form Im cosine omega t plus theta I. We know that we can represent these signals using an exponential form complex number. So this is the same as the real part of Vm e to the j omega t plus theta v. And similarly, our current is the real part of Im e to the j omega t plus theta I, right? We're going to reuse these representations of our voltages and currents for everything that we're doing here for the next several minutes, but I just want to be explicit about what it is that we're doing. All right, so what is the relationship between voltage and current for a resistor? Not meant to be a trick question by any shape or form. Ohm's law. Thank you, Devarier. You're right. You're absolutely correct. So Ohm's law tells us that V of t is equal to R times I of t. So what we're going to do now is we're going to substitute in our complex number representation of V of t and I of t, and then derive what the relationship will be in the frequency domain. Okay. So our voltage signal, Vm e to the j omega t plus theta v, will be equal to R times Im e to the j omega t plus theta I. What I'm going to do now is simply split these exponential representations up. So I'll have Vm e to the j omega t times e to the j theta v is equal to R times Im e to the j omega t e to the j theta I. And we can see that the frequency term e to the j omega t goes away. What this leaves us with is Vm e to the j theta v is equal to R Im e to the j theta I. So at this point, we're going to focus on this last expression here, and we're going to look at it from two different perspectives that are really kind of the same thing. Okay. So the first way that we're going to interpret this, on the left-hand side of the equal sign, we have an exponential form complex number, which has a particular magnitude and a particular phase angle. Well, on the right-hand side of the equal sign, we also have an exponential form complex number. So the magnitude on the left-hand side has to equal the magnitude on the right-hand side, which means Vm is simply equal to R times Im, and the phase angle on the left-hand side has to equal to the phase angle on the right-hand side, which means theta v must be equal to theta I. So we now have some simple rules that tell us what our magnitude is in terms of the other quantities, and we also know how to find our phase angle. Another way that we can look at this is to observe that our polar form complex number, excuse me, our rectangle, oh gosh, our exponential form complex number only contains a magnitude and phase angle component. So we could rewrite it in polar form as Vm angle theta v without losing literally any information whatsoever. Similarly, on our right-hand side, we're going to have R times Im angle theta I. Well, this guy right here is just phasor voltage V, and this guy right here is just phasor current I. So we can say then that in the frequency domain, V is equal to R times I, or Ohm's law in the frequency domain works exactly the same way as Ohm's law does in the time domain. We just get to use these phasor representations, okay? So that tells us a bit about how resistors behave in the frequency domain. We're going to follow a similar treatment for inductors and capacitors. So for an inductor, of value L has a voltage drop V of t across it and a current I of t flowing through it, we know that the voltage drop across the inductor, V of t, is equal to L times di by dt. Using our exponential form complex number representation of our voltage and current, this looks like Vm e to the j omega t plus theta v is equal to L times the derivative of Im e to the j omega t plus theta I. So let's keep on trucking here. On the left-hand side, we still just have Vm e to the j omega t plus theta v. On the right-hand side, when we take the derivative of e to the j omega t plus theta I, that's simply multiplying by a factor of j omega. So we're going to have j omega L times Im e to the j omega t plus theta I. And now I'm going to split my exponential function up again. So this gives me Vm e to the j omega t e to the j theta v is equal to j omega L Im e to the j omega t e to the j theta I. We're going to cancel out or suppress our frequency terms again, which means we're effectively working in the frequency domain now. And what we observe is that Vm e to the j theta v is equal to j omega L times Im e to the j theta I. On yesterday's lecture, I believe I talked about how we could represent multiplying by a factor of j is the same thing as multiplying by a factor of 1 e to the j 90 degrees. We got that result by looking at the number j on the complex plane and then representing that complex number in an exponential form. Okay. So what that means is I could rewrite this expression as omega L times Im e to the j theta I plus 90 degrees. From this, we can observe that our magnitude of our voltage Vm is equal to omega L times Im, and we can see that theta V must be theta I plus 90 degrees, meaning that there's always a 90-degree phase difference between the current and voltage in an inductor. We can also observe by relating our voltage complex number as a phasor, Vm angle theta V will be equal to j omega L times Im angle theta I. And so we get the relationship V is equal to j omega L times I. So this is our current voltage relationship for inductors in the frequency domain. Capacitors are going to be very similar. So for capacitors, where we have a capacitance value C, a voltage V of t, the current I of t, we know that I of t is equal to C dV by dt, and therefore Im e to the j omega t plus theta I is equal to C times the derivative with respect to time of Vm e to the j omega t plus theta V. Since we did something incredibly similar to this just a few moments ago, I'm going to effectively combine two steps into one. I'm going to take my derivative here, which is just multiplying by a factor of j omega, and I'm also going to split up my exponential function, which is going to give me Im e to the j omega t e to the j theta I is equal to j omega c Vm e to the j omega t e to the j theta V. We have that frequency term show up on both sides again, so we can throw away that redundant information. And we are left with Im e to the j theta I is equal to j omega c times Vm e to the j theta V, which could be expressed as omega c Vm e to the j theta V plus 90 degrees. From this representation, we observe that Im is equal to omega c times Vm, and theta I has to equal theta V plus 90 degrees. From this representation, we observe that Im angle theta I is equal to j omega c times Vm angle theta V, or I phasor is equal to j omega c times V phasor. So this is our current voltage relationship for capacitors. I'm going to put a box around this equation, this equation, and this equation, because we're going to revisit these in just a moment. So we are almost through laying down the fundamental groundwork for circuit analysis in the frequency domain. The last thing that we need to do is introduce the concept of impedance. So impedance is the frequency domain equivalent of resistance. Okay, so let me explain what I mean by that. As a very brief review, we found much earlier in this class, I believe on the third class meeting, that if we had a linear black box network and we applied some type of DC source, doesn't particularly matter whether it was a current source or a voltage source. If we measured the voltage drop across the terminals of the linear black box network, and we measured the current flowing into the linear black box network, the resistance of the linear black box network was given by the ratio of V over I. If we do the exact same thing with a sinusoidal source, so if we take our linear black box network, but this time we apply a sinusoidal source. Again, it does not matter remotely if it's a current source or a voltage source. And we measure a phasor voltage across the terminals of the linear black box network and a phasor current flowing into the linear black box network. We can define the impedance Z as the ratio of the phasor voltage to the phasor current. Okay, so impedance plays the role of resistance. Okay, they are equivalent just in two different domains. Okay, now our impedance Z by definition is simply the ratio of phasor voltage to phasor current. Because our impedance is the ratio of two complex numbers, impedance itself is also a complex number. And it can be represented in either a polar form or a rectangular form. So let's start with the polar form representation. So our phasor voltage V is Vm angle theta V. Our phasor current I is Im angle theta I. And therefore, we have a magnitude of Vm over Im and a phase angle of theta V minus theta I, which we could more easily call the magnitude of Z angle theta Z. That's our polar form representation. Our rectangular form representation breaks our impedance up into two parts. Resistance R plus JX, okay? So this is the resistance, and resistors contribute to this portion of the impedance. X over here is what's called the reactance. And this is where inductors and capacitors contribute to the impedance, okay? So the real part of impedance is simply resistance, and that is literally just resistors. And then the imaginary part of impedance is what's called reactance, and that's made up of both inductors and capacitors. Okay. So we're going to use the fundamental definition of impedance to find the impedance for resistors, capacitors, and inductors. So for a resistor, the impedance of the resistor, ZR, is just the ratio of phasor voltage V divided by phasor current I. So I'm going to scroll up here for our phasor relationship. And if we divide both sides by phasor current I, we'll see that phasor voltage V divided by phasor current I is simply R. So the impedance of a resistor is the resistor value itself. Obviously, this is measured in ohms. Okay. Now, I'm going to more formally write this impedance as a rectangular form complex number. So this is going to look like R plus J 0 ohms. And I'm also going to more formally write it as a polar form complex number, which would be R angle 0 degrees ohms. So these are the three different ways that we could express the impedance of a resistor. For an inductor, if we scroll back here, if we divide our phasor voltage V by our phasor current I, what we're left with is J omega L. From that, the impedance of an inductor is J omega L. I'm going to come down here a little bit, and we're going to play with these units, okay? So omega has units of radians per second. Inductance L has units of henries, where a henry is equal to a volt second per ampere. So when I multiply these together, omega times L, what I get is radians per second multiplied by volts seconds per ampere. Well, the seconds cancel each other out, and radians is a dimensionless quantity. So I just have units of volts per amp, which is the ohm. So the impedance of an inductor is also measured in ohms. In rectangular form, this looks like 0 plus J omega L ohms, which means an inductor will always have a positive reactance. In polar form, this looks like omega L angle positive 90 degrees ohms. For a capacitor, we go back up here. Our relationship is phasor voltage phasor current I is equal to J omega C times phasor voltage V. Algebraically rearranging this, we find that V over I is equal to 1 over J omega C. Let's look at the units here. So omega is obviously still measured in radians per second. Capacitance is measured in farads, which is the same as an amp second per volt. So we are going to have 1 over omega c, which is going to look like 1 over radians per second multiplied by amp second per volt. The seconds cancel. Radians is a dimensionless quantity. We have 1 over amps per volt, which is a volt per amp, or an ohm. In rectangular form, this comes out to be 0 minus J times 1 over omega c. So what I've done here is I've effectively used the identity J to the minus 1 power is the same as negative J. I've done this to show that capacitors should always be contributing negative reactance. Okay. In polar form, this looks like 1 over omega c angle minus 90 degrees ohms. Okay. So before we move along to actually analyzing a circuit, I want to point something out here. The impedance of a resistor, a capacitor, an inductor, or any combination thereof is always measured in ohms. What that implies is that impedances combine like resistances. Or in other words, we no longer have to worry about special rules for combining capacitors, combining inductors, etc. In the frequency domain, everything behaves like a resistor. It just happens to have an imaginary component to it. All right, so what we are going to do now is tie all of this stuff that I've talked about together here and rework the circuit that we looked at in class yesterday twice. The first time we analyzed it, we did so in the time domain, and it took us about 20 minutes. The second time we analyzed it, we did so in the mixed domain, and it took us about 5 minutes, 5 or 6 minutes. Now we're going to analyze it in the frequency domain, and I'm going to show you that once we convert our circuit to the frequency domain, we can do our analysis in less than a minute. So our circuit of interest is once again this guy, where we have our sinusoidal voltage Vs of t connected to a 10 ohm resistor, which is in turn connected to 25 millifarad capacitor, and our goal is to determine this current I of t, where if Vs of t is equal to 12 cosine 5t plus 10 degrees volts, we are expecting our current I of t to be of the form Im cosine 5t plus some phase angle theta I. Okay. Our first step in performing our analysis in the frequency domain will be to convert voltages and currents into phasors. So for now, we're going to leave this resistor as a 10 ohm resistor. We're going to leave this inductor as a 25, capacitor as a 25 millifarad capacitor. So the first thing that we're going to do is we're going to convert our time domain voltage, Vs of t is equal to 12 cosine 5t plus 10 degrees volts, into a phasor. How do I do that? So nobody's answering. So let's scroll back up to the first thing that we covered today. So how did we do it in this example problem? We kept the magnitude and we kept the phase angle and we threw away everything else, okay? So our magnitude is 12, our phase angle is 10, so our phasor voltage is just 12 angle 10 degrees volts. The phasor current we're looking for is now just phasor current I, and we're done with step one. Step two will be to convert resistors, inductors, and capacitors into their equivalent impedances. So the impedance of a resistor is just the resistor value, which means that 10 ohms stays 10 ohms. For our capacitor, the impedance of a capacitor is 1 over j omega c. So this is going to look like 1 over j times omega is 5 times c is 25 times 10 to the minus 3. This is going to look like negative j 8, I believe, but I want to make sure. So 1 over 5 times 25 times 10 to the minus 3. Yeah, 8. Minus J8 ohms. So we're going to simply scratch this out and put minus J8 ohms here. And now we're ready to do our analysis. We can use any of our DC circuit analysis techniques that we have learned to solve this problem. Okay, so I'm going to use Kirchhoff's current law. I'm going to say that phasor current I is equal to the sum of phasor current IR plus phasor current IC phasor current IR is 12 angle 10 degrees volts over 10 ohms. Phasor current IC is 12 angle 10 degrees volts over impedance negative J8 ohms. And now I'm just going to throw this into my calculator. I have 12 angle 10 over 10 plus 12 angle 10 over minus 8I is equal to 1.921 angle 61.340 degrees amps. And now I'm going to convert my phasor back into a time domain signal. So I of t is just 1.921 because the magnitude stays the same, cosine 5t plus 61.340 degrees amps. This is the exact same result that we got working this problem the other two ways, but from an analysis perspective, we did it in one line, really two lines after we used KCL in a general form, and then we plugged in numbers, and then we threw it on our calculator and got the answer that we were looking for. So we've taken tens of minutes of work in the time domain and crunched it down to seconds of work in the frequency domain. Okay? So this is our plan of attack for any and every sinusoidal circuit that we see. Okay? We convert all of our voltages and currents into phasors. We convert all of our resistors, inductors, and capacitors into impedances. And then we use whatever DC circuit analysis technique we feel like to get the result we're looking for. Everything is back on the table. Ohm's law, Kirchhoff's current law, Kirchhoff's voltage law, source transformations, source combinations, nodal analysis, mesh analysis. All of these are fair game for doing circuit analysis in the frequency domain, as long as we take care of these first two simple steps first. Okay. So what I want to do for the remainder of today's class meeting, as long as you guys are willing to listen to me talk, is just work a couple of example problems and take some feedback from you guys as to how we might solve for things. Okay. So let's look at a problem that is arguably, or at least it's going to look significantly more difficult than that short little example that we just worked. Okay. So let's say that we have the following circuit wherein we have a voltage source, Vs of t. Here we have 5 ohm resistor. Here we have 4 Henry inductor. Here we have a 0.2 farad capacitor. Here we have a current source, Is of t, and our goal will be to find the voltage drop across this inductor, where Vs of t, so let's make it 20 cosine 2t volts, and Is of t will be 3 sine 2t amps. Okay. So I'm expecting you guys to give me some sort of feedback here, all right? The first thing that we're going to do is we are going to convert our voltages and currents into phasors. So what's the phasor representation of Vs of t? ∠0. Thank you very much, Devarier. Over here, I'm going to have my current source. Let me at least put the symbol down for my resistor, my inductor, and my capacitor. How do I represent Is of t as a phasor? ∠-90 degrees. Thank you, Sydney. Absolutely correct. And a very good catch that you realized you needed to convert the sine function into a cosine function. So, excellent job. I was expecting to trip you guys up there. So very, very good catch. All right. What's the impedance of our resistor going to be? Five ohms. Absolutely right, Justin. The impedance of a resistor is just the resistor value itself. No work or thought needs to go into that. What is the impedance of our capacitor going to be? So just to refresh your memories, the impedance of a capacitor is 1 over j omega c. In case you're wondering on where to find omega, it's that guy right there, the 2 that's in front of the t in our sinusoidal signals. So not quite. And I might have done my mental math here incorrectly, so let me talk my way through it, okay? So omega is 2 and c is 0.2. So omega times c is 0.4. I agree with that wholeheartedly, but it's 1 over that. So 1 over 4/10 should be 10/4, which is 2.5. So I believe the correct answer is -j 2.5 ohms. By all means, throw it into your calculator and make sure that my mental math is correct. So 1 over 2 times 0.2 is 5/2 or 2.5. Somebody else tell me what the impedance of my inductor is, where the equation is simply impedance of an inductor is equal to j omega L. 8J, thank you, Devarier. All right, so that's our circuit. This is the quantity that we're trying to find. So how can we do it? Somebody just throw an analysis method out. Nodal, okay. Justin, which, let me identify my nodes here. So there's 1, there's 2, there's 3, here's 4. Which of these 4 nodes do you want to be our reference? The bottom. Okay, that's a very reasonable choice. It's absolutely what I would have chosen. So I'm going to do something here, which I'm going to call modified nodal analysis, okay? We could do a full nodal analysis thing here. But the problem if we did a full-on nodal analysis would be that our calculators are incapable of solving a system of complex equations, okay? So I'm going to very slightly modify how we're doing this analysis, okay? Let's say that this was our phasor voltage VA. This was our phasor voltage VB. And this is our phasor voltage VC, okay? So if we did conventional nodal analysis, we would have a voltage relationship equation that would be VA is equal to 20 angle 0 degrees volts. And then we would have a KCL at node B equation that would be VB minus VA over 5 ohms plus VB over J8 ohms plus VB minus VC over negative J 2.5 ohms is equal to 0. And then we would have our KCL at node C equation, which would be VC minus VB over negative J 2.5 minus 3 angle negative 90 degrees amps is equal to 0. And then we'd have to use a computer to effectively solve this system of equations. Okay, there's nothing remotely wrong with that for your homework or anything like that, because you're allowed access to your computer. For an exam where a problem like this would absolutely be fair game, though, we couldn't do this full-on nodal analysis like this, because to do so, we would have to use Kramer's rule or something like that and effectively solve this system by hand, which would just take too damn long, okay? So instead, on the right-hand side here, I'm going to do what I called modified nodal analysis, okay? And so what I mean by modified nodal analysis is we're just making some simple observations here. So the first observation that we could make is that VA is just 20 angle 0 degrees because of where we chose our reference node. Another observation that we can make is that the current that's flowing through our capacitor is 3 angle negative 90 degrees amps. So what I'm going to do is I'm going to write a Kcl equation at node B, and that's it. But I'm going to write this Kcl equation with those observations that I've made in mind. So to be very clear here, I'm simply adding this current together, this current together, and this current together. Well, the current directed to the left through the 5 ohm resistor could be expressed as VB minus 20 angle 0 degrees volts over 5 ohms. The current directed down could be expressed as VB over J8 ohms. And the current directed to the right through the capacitor could be written as negative 3 angle negative 90 degrees amps. And I set this equal to 0. So I've done nodal analysis here, but I've put in those useful pieces of information, which have allowed me to write an equation that has only one unknown quantity. And I can easily solve this using algebra, right? So for instance, I can factor out VB. So I will have 1 over 5 ohms plus 1 over J8 ohms. And then I'm going to move my constant terms to the right-hand side. So this is going to look like 20 angle 0 degrees volts over 5 ohms plus 3 angle minus 90 degrees amps. Well, that's a complex number I can throw in my calculator. So 1 over 5 plus 1 over 8i is 0.236 angle negative 32.005 degrees. I can throw all this junk here in my calculator as well and just come up with a single complex number. So I have stored this in my calculator as A. When I put the stuff on the right-hand side, so that's 20 angle 0 over 5 plus 3 angle negative 90, that comes out to be 5 angle negative 36.870 degrees. And I'm going to store this in my calculator as B. Now I can see that VB is just what I have stored as B divided by what I have stored as A. Which comes out to be 21.2 with an angle of negative 4.865 degrees. volts. Well, our phasor voltage VB is the exact same thing as our phasor voltage VL. VB is a nodal voltage measured from the green node with respect to ground. And VL is a voltage between the green node and the blue node, which is effectively the exact same thing as VB. So VL is 21.2 angle negative 4.865 degrees volts, and VL of T is just 21.2 cosine 2t minus 4.865 degrees volts. Okay. So did that modified nodal analysis make sense there? We just made two observations that I believe were pretty straightforward, and it allowed us to effectively eliminate two of our three equations in our system and give us a simple one equation, one unknown thing that we could solve algebraically in a relatively straightforward fashion. By the way, that is not the only way that we could have solved that circuit to get the same result. We could have used superposition. In using superposition, that would allow us to practice voltage division and current division to find out what that VL is. We could have done a trying to think if we could have done source transformation here on the practical voltage source on the left-hand side to do any simplification there. That might make the problem actually a little bit more difficult. We could actually use Thevenin and Norton equivalent circuits to solve for this thing. So we'd find the Thevenin equivalent voltage from the perspective of the inductor, the Thevenin equivalent impedance from the perspective of the inductor, and or the Norton equivalent current from the perspective of the inductor, and then effectively simplify the circuit into a practical voltage source connected to the 8 ohm inductor, or a practical current source connected to the 8 ohm inductor, where we can then just use voltage division or Ohm's law. Effectively, there's going to be about 5 to 6 different ways that you could theoretically solve any circuit that I'm going to give you on the exam. And you just need to figure out which method you are most comfortable with, and then put the work in to make sure that you're handling all of the complex number portion or all the bookkeeping correctly. That's where the overwhelming majority of your mistakes are going to come from, is small calculator errors and things like that. At this point, using nodal analysis, mesh analysis, KVL, Kcl, Ohm's law, current division, voltage division, all of those things, you should be pretty familiar with. You may not be masters of them all just yet, but you should know what they are. At this point, it's just practicing them again using complex numbers. So with that in mind, what I typically do on the next lecture, which we'll be having Thursday, is literally just work a few example problems to reinforce circuit analysis concepts that we haven't used in a while. So you guys tell me what you want to have reviewed, and that's what we'll review. All right, Devarier, we'll, on Thursday, we'll do some voltage and current division. Anybody else have a suggestion? All right, so it looks like Thursday's lecture will be fairly brief. I'll work a problem R2 that involves the use of voltage and current division in the frequency domain, just to really kind of show you guys how it's done. If on Thursday you think, oh, actually, Dr. Hartman, maybe you could run through something using superposition, maybe you could do source transformation or whatever, just let me know and I'll make up a problem and we'll work it there. I have talked for enough for today, so I hope you guys have a great rest of your afternoon, and I will see you on Thursday.